In a previous video, we looked at the best path for a defensive back to take to catch a ball carrier, but the path was a high-risk, high-reward path. What if the defensive back isn't sure if it's even possible to catch the ball carrier? Or what if the DB is willing to give up some yards to have a better chance of getting the tackle? Which direction should he go then? Welcome back to Math of the World. In the last video, we derived the ideal path for a defensive back using geometry, and assuming the defensive back and the ball carrier were the same speed. We used a perpendicular bisector to find a point on the sideline to run to. We called this ideal path the isosceles triangle path because of this triangle here. We also learned that the DB can pay attention to the swivel of his head to know if he's on track to make the collision. Today's question is about finding the safest path, or a path that would give the best chance of catching the ball carrier if the DB's caught out of position. Let's go back to the mathematical model we developed in the truck evasion problem. This function takes an angle as an input and has time as the output. The extra time the DB would wait until the ball carrier got to his position. We used this model to find the angle a pedestrian could take to give them the most time to evade a truck. Taking the same approach doesn't help here because if the DB and the ball carrier have the same speed, then the model says to go straight down the field and not run towards the ball carrier at all. Following that strategy is going to get that DB pulled from the game immediately. So let's take a different approach. If there is a possibility of the DB catching the ball carrier, there's probably more than one path the DB could take. There's this optimal path that maximizes the time between getting to the sideline and the ball carrier getting to the DB, but in most cases, the DB could also catch the ball carrier by going a little one way or the other from this optimal path. So if there is a possibility of making the tackle, there are probably a lot of paths the DB could take. These paths are represented by the angles that make the value of our function positive, because that means the DB would get to that spot with time to spare to make the tackle. Any angle between these two paths is a viable angle to take. But depending on the distances involved, that set of angles could be large or small. How can the DB know which angles may lead to a tackle? Or is there a way to always find at least one such angle? Let's move the ball carrier down the field. As we do so, it'll be harder and harder for the DB to get to the ball carrier in time. Eventually, there will only be one solution. If the DB could find this solution, then no matter where the ball carrier is, this is the best chance to get a tackle. In order to find this path, we must ask ourselves, is there anything special about this path? Right at this moment, when there's only one possible angle to make the tackle, the angle the DB takes looks like 90 degrees. We can actually check this. We could use trigonometry, or we could use vectors and dot products, and find that it is indeed 90 degrees. Let's use the values from the previous truck evasion video. We will move the ball carrier down the field until there's only one possible path, one last possible moment for the DB to make the tackle. We can show that this angle is 90 degrees using trigonometry by cutting the angle up into these two pieces. The upper part we can calculate with arctangent and these distances. And we learned in the previous video that this path is the arcsine of the ratio of the two speeds. Notice that they sum to something very close to 90 degrees. Well, the defensive back doesn't know if it's the last moment or not, and isn't going to stand around guessing, but the DB can assume that any moment is the last possible moment and take the perpendicular path anyway. It's not always the optimal path in the sense of the pedestrian getting to the curb with the most time to spare, but it is always one possible path if a possible path exists. Here's one thing that might convince you that this claim is correct. In this animation, we have all possible angles the DB could take to make the tackle. We also have the perpendicular path. Notice that the perpendicular path seems to always stay in the interval of possible angles. This is quite a claim we're making, and a visual justification still might not convince you, so we provide a mathematical justification at the end of the video. So we now have a safe path the DB can always take. This path perpendicular to the line between the DB and the ball carrier. This is independent of speeds or position. This path will always be a direction that will get the tackle if there is any possibility of making the tackle. But this safe path can also be used in other situations, sports or otherwise. Back in the truck evasion problem, we found the optimal angle for my daughter, Sarah, was 18.6 degrees, but that optimal angle depends on the speeds of her and the truck. But if she takes a perpendicular path from the line between her and the far side of the truck, then that gives her a safe path for escape, as long as there is one. In the soccer situation, perpendicular is right down the goal line, so this is one argument for jumping down the line, although there are other considerations in soccer which we address in another video. Pursuits in hockey or soccer can use the same perpendicular path strategy, or even a parent chasing a child who's heading into the road. So let's recap where we are at. The DB can take the isosceles triangle path. That gives the DB the chance for making the earliest tackle, assuming the speeds of the athletes are about the same. Or the DB can take the safe path, this perpendicular path, which works no matter what the speeds are. The isosceles triangle path is the furthest upfield the DB should go, and the perpendicular path is the furthest downfield. As long as it isn't past the goal line, then they can head for the pylon. No matter what direction the DB takes, he should pay attention to the swivel of his head as he runs in order to make adjustments. If the DB is heading in the perpendicular path and his head is swiveling downfield, he's too far out of position or not fast enough to catch the ball carrier anyway. The geometry of the situation gives another way for the DB to find the isosceles path. The isosceles path leads to a point that's halfway between the ball carrier and the point where the perpendicular path intersects the sideline. That might be easier for the DB to think about than trying to picture the perpendicular bisector. That wraps up the football situation. We end this video with a mathematical justification that the perpendicular path is always a possible tackling path if there exists at least one tackling path. Our assumptions about the situation are that the players are running at a constant speed, but their speeds don't have to be equal, and that the ball carrier will continue to run down the sideline, not changing directions, and that neither runner is impaired by other players. We also assume that if the DB gets to the sideline before the ball carrier, they'll make the tackle. Let's start by supposing there's one possible tackling path that's not the perpendicular path. For example, the path along the optimal angle that gets the DB to the sideline with the most time to spare. We will call this path O for optimal. Now we will construct two other paths on this diagram. One is the perpendicular path from the DB's position. The other is a perpendicular path that ends at the tackle. We call these paths A and B, and we want to show that A is also a path the DB can take to make the tackle. We will call this distance L, the distance from the ball carrier down to where A intersects the sideline. The general argument we'll make is that if the DB could make the tackle on the optimal path, then the DB could also make the tackle by taking B, if they were here, and if they could make the tackle along B, then they can do it by A, which is what we're trying to show. The first thing I'm going to argue is that paths A and B are either both tackling paths or both missed tackle paths. This can be justified using similar triangles. If the DB could catch the ball carrier by taking A, then the time calculated by dividing the length of L by the speed of the ball carrier is smaller than the length of A divided by the speed of the defensive back. Since these two triangles are similar, the lengths are proportional, so this new length is a scaled version of L, and B is a scaled version of A with the same proportion. We can call it P. But all this is done is multiply each side of the inequality by a constant, which maintains the inequality if the constant is greater than 0. So B is also a tackle path. The argument works the same if we start with the assumption that B is a possible tackle path to show that A is also then a possible tackle path. So both A and B are either tackle paths or neither is a tackle path. Now we'll show that if O is a possible tackle path, so is B. Notice that B is shorter than O because O is a hypotenuse of a right triangle and B is a leg of the same right triangle. And the legs are always shorter than the hypotenuse. So if the DB could tackle the ball carrier by taking O, then the DB could also do it if he started from here and took B, because B is a shorter path than O and they end up at the same spot. So if O is a possible tackle path, so is B. And we already know if B is, then so is A, which is the perpendicular path. So no matter what, if there's a possible tackling path, the perpendicular path will also be a possible tackling path. When did you find yourself using math you didn't think you would ever use? I was once in a consultation meeting where someone was doing research on business networks, and I was able to offer help in the form of a theorem that gave bounds on eigenvalues of symmetric matrices. I didn't think that would ever come in handy, but it did. Thank you so much for watching. Please subscribe and share our videos.